Okay, so next we're going to talk about mutual inductance. So mutual inductance is when you have two coils that are relatively close to one another, and these two coils, where one of them has a current initially running through it. So let's take here to be coil one. So you can see, right, there's a current at the top coming out, at the bottom going in. So this current in the coil one generates magnetic field. Those blue, the green lines are the magnetic field generated by coil one. This magnetic field, so let's call this P1. Okay, this magnetic field then goes through the coil two, basically to the center of the coil two. Okay, now as the magnetic field through the coil two, we can look at it in terms of it can be combined with the area of coil two to see that there's a magnetic flux through the coil two. So you can say that there is a magnetic flux through the coil two. And what we can say here is that here's a magnetic flux. All right, so this is that coil one, basically generates in coil two. Okay, so this is magnetic flux P12. Why? Because there's a magnetic field B2, right? And there's an area of the coil two. Sorry, there's a magnetic field one through the area of coil two. So there's a magnetic flux. All right. So, but the magnetic flux alone will not induce current, right? So remember, you can have a magnetic flux, but if the current is constant or the magnetic field is constant, nothing happens. There is no induced EMF or current. What we need to do is vary the current through the coil one. So that means this current through the coil one, if it's variable, that means it varies with time. That means the magnetic field that it generates also changes with time. Okay, remember, so magnetic field is going to be variable, and this was equals to mu naught I, assuming that n is just basically constant, divided by 2r. So let's say that's the magnetic field strength at the center, that it generates, right, for the coil one, and if n represents the number of turns for coil one. So this is the magnetic field. We can see that it depends on I1. So, but if magnetic field is due to a time varying current, that means you have mu naught n1 over 2r. R1 is the radius of the coil one, but then let's say di dt. Okay, so it's a varying, let's say current. Then obviously, then the magnetic field starts changing. As the magnetic field starts changing, so does the flux. That means there's also change in flux. But what we have here is the magnetic field B1. Since there is a flux through the coil 2, and assuming that whenever you see a lowercase I, so this I1, since it's lowercase, it means it's a time varying current. That means it's either increases or decreases, but it's changing with time. So then we can calculate what we call mutual inductance, M12, and this will be equals to the N2, which is number of turns for the coil 2, and 1 will be number of turns, right? Here, basically it's written there. So N2 times then the flux 1, 2, and divided by I. I is the time varying current in coil 1. So this will be then in terms of mutual inductance through the coil 2. All right. So one thing we have here is that this, as the magnetic flux through the coil 2 starts changing, coil 2 then induces current and EMF. That means there's going to be a time varying current 2 inside the coil 2, which in turn will generate its own magnetic field, which will go through the coil 1, and then the coil 1 will induce then its own magnetic field. So that's why it's mutual inductance. So coil 1 first induces, EMF and current in coil 2, and as the coil 2 starts generating its own magnetic field that goes through the coil 1, then it's going to generate induced EMF and current in the coil, let's say coil 1. All right, so M12 of coil 2, this is the mutual inductance, M12 of coil 2 with respect to coil 1. All right, so again, so written like this. Um, Now, one of the things we can talk about here is that, as I said, right, so you're going to have then induced EMF in coil 2 due to the fact that the flux will be changing. Again, we're assuming that you can calculate the mutual inductance in terms of the flux, not time varying flux, but let's say the flux, right? But then one thing we have here is if you have flux that is changes with time, so d b dt, remember the Faraday's law tells you that induced EMF is equals to negative n times change in flux with respect to time. That means, for example, let's calculate what will be induced EMF in coil 2. Okay, that means what we do here, we come back here and say, okay, we're going to look at, induced EMF coil 2, and this will be because there's a induced, basically there's a change in flux due to the coil, coil 1. So basically 1, 2. So now that means what we need to do is take this equation for the mutual inductance, rearrange. That means first we take what the flux F12 is. So flux F12 is going to be equals to, rearrange this. So it's going to be mutual inductance of 1, 2, then times current 1, then divided by N2, which is number of turns in coil 2. Okay. Now, let's then assume that there's a change in flux. Why is there a change in flux? Because current is changing. Okay. That means we can then apply this where I can say that going, taking this equation over there and plugging it into the EMF equation, I can say then EMF2 is equals to negative number of turns, then times change in flux. What is flux? Is mutual inductance 1, 2 times current 1 divided by number of turns. So technically this is number of turns in coil 2 over here, since it's EMF2. So like that. So that means this is basically the flux. And what we can see here is, since I have negative number of turns in coil 2, mutual inductance is a constant, so it can come out of the, from the derivative. So it becomes, M12. N2 is also a constant. It can come out. So N2. And then what we end up with here is then di1 dt. Okay. Obviously, you can see that we can get rid of the N2. So then EMF2 is equals to then negative M12 times di1 dt. That means we can see from here is that EMF2 is equals to the negative of the mutual inductance times di1 dt. All right, so that's kind of what we can do. And we can also assume that once the EMF and current is induced in coil 1 as well, after, let's say, the coil 2 generates its own magnetic field, and the magnetic field, let's say B2 will go like this, and then it will generate EMF in coil 1. We can say that if we look at the mutual inductance of M12 and M21, then mutual inductance of coil 1 and coil 2 is exactly the same as coil 2 and coil 1. Okay, that means what we can do here is we can say EMF 2 is equals to negative M12 or M21. So technically we can just drop the subscript. We can say M12 is equals to M21 equals to just M, mutual inductance. So this is this negative M, then times di1 dt. That means we can see that this is basically the equation for the induced EMF in coil 2. Similarly, I can then say induced EMF in coil 1 will be equal to the negative M, then di2 dt, because then I2 is a time varying current in coil 2, which in turn will induce EMF in coil 1. Okay, so that's kind of, what we end up having. So that means these are the equation for the EMF for the two coils that mutually, induce current and EMF on one another, and the mutual inductance is exactly the same for both coils. All right, so there you go. So that's basically in terms of, you can see right what we have. All right, so one important thing to see from here is that EMF2 and EMF1, they are not proportional to the current 1 and current 2, but derivative of current 1 and current 2. That means there has to be changing current. There has to be changing current in order for there to be EMF. If the current is constant or already reached its maximum value, then the current, basically the derivative of that is 0, right? So what we get here is we get no EMF2 and no EMF1. Let's look at an example here. We have two coils that have mutual inductance, M equals 3.25 times 10 to the negative 4 Henry. By the way, the unit of mutual inductance is the same as self-inductance, which is Henry. So the current I1 in the first coil increases at the uniform rate of 830 amps per second. What is the magnitude of the induced EMF in the second coil? And is it constant? All right, so let's look at this part first, and then we'll go to the part B. We are given that mutual inductance is 3.25 times 10 to the negative 4 Henry. And we're told that the current has a uniform rate of 830 amps per second. That means it's di1 dt is equals to 830 amps per second. All right, so that's good enough for me to calculate induced EMF in the second coil. Induced EMF in the second coil equals negative M times then di1 dt. So again, if you want, you can put the negative, you don't have to put the negative. Let's say you can pretty much take an absolute value, because what we're just calculating here is the value of the EMF. Doesn't matter if it's clockwise or counterclockwise. So this will be 3.25 times 10 to the negative 4 Henry, and then times 830 amps per second. All right, so once we do this calculation, then we can calculate the induced EMF in coil 2, and this will be 0.270 volts. Okay, now let's answer the second part of the question, or second question, that part. Is it constant? Well, let's see what we have. We're told that EMF2 is equals to 0.270 volts. What will be the EMF 1 second later, 2 seconds later, 1 minute later? Well, we can see that EMF2 does not depend on time. That means there is no time dependence for the EMF2. So we can say that this is constant. Now, how do we know there's a time dependence? Well, it would be time dependent if, let's say, the value was EMF2 is equals to 0.270 T volts. That means you can see, right, in this case, when T equals 0, EMF2 is 0. When T equals 1, then it's 0.270 volts. When it equals 2, then double that, and so on and so forth. Now, how can we have an EMF that is time dependent? Well, let's go back to look at the equation. Equation, we have a mutual inductance, which is never time dependent, just a constant value. Then times the rate at which the current is changing, which is 830 amps per second. Now, when you go back and look at the rate at which the current is changing, the problem directly tells you that it increases at a uniform rate, which means that this di dt is basically a constant itself, right? It's 830 amps per second. That means, for example, if di dt was 830 t amps per second, that means it increases with time, right? When t equals 0, it was 0. When t equals 1, it's 830. When t equals 2 seconds, it's 830 times 2. T equals 3 seconds, it's 830 times 3. That means di dt itself is changing, time dependent. Then if imagine, right, if I come back and plug in this one over here like that with a t, then this would have been with a t, and I would have had then time dependent EMF. But it's not, because there is no t, so it is uniform, right? It's a uniform rate. That means every second current increases by 830 amps. 1 second is 830. Next second it increases by 830. Third second is increases 830 on top of what it was before. So the rate at which it's changing is constant, means EMF is always going to be constant. Part B says, suppose that the current described is in the second coil rather than the first. What is the magnitude of the induced EMF in the first coil? Well, let's call this part A. Part B. Here what we have is this. Let's say if I'm doing EMF1, it equals to negative M, or let's, get an absolute value. So M times then di2 dt. But we're saying that the current described is in the second coil. That means exactly the same current, which means if I plug in same M, same di dt, I'm going to get, 0.270 volts. Same thing as before. Okay. That means what we're here, the question is saying the same current rate, mutual that is already the same. That means nothing will be different about EMF in the first coil. All right. Now let's look at what we call LC circuits. So the LC circuit is L for the inductor, self-inductance, right? And C is for the capacitance. So then what we have here is we have a circuit where there's a battery and we have two devices, which is an inductor and a capacitor. Our circuit does not have a resistor. So just an inductor and a capacitor. And one of the things we have a switch that can be thrown into two different positions, A and B. First, we start with switch thrown at A. When it's thrown at A, in a way, then this basically becomes nothing. Okay, so that's, open circuit there. So what we'll have here is there's going to be a current, and the current here will go like this. Okay, and we have just a capacitor in the circuit. Okay, that means there with no resistance. What we also have here is there's also basically no inductor at this part, because the inductor is pretty much out of the circuit because the way we designed the circuit. And what we're going to do here is just basically have a process of the charging of the capacitor. Okay, that means what we have here is at some point, then the capacitor will be fully charged, and then the energy will be stored in an electric field of the capacitor. Okay, so just a simple, charging of the capacitor, which we've seen, in the previous chapters and also in the labs. Okay, so let's say, at this point, we just have a capacitor fully charged. And remember what happens, right? So when a capacitor is fully charged, what we have here is this. So the current as a function of time is equals to maximum current times e to the negative t over tau. Okay, so that means the current basically, pretty much goes to zero, right? As the capacitor becomes fully charged. So in terms of then what we have here is, as the capacitor is fully charged, then we can say that this is basically, current here is equals to zero when the capacitor is charged. Okay. When capacitor is charged. And all the energy here is that provided by the battery, then, all the potential energy is stored in the capacitor. Okay. Now, what we can do after that, by the way, this is the amount of energy, right? Amount of the energy that was stored, which is UE equals Q max divided by 2C, which is, this is in terms of the maximum charge squared divided by 2 times the capacitance. We've seen this before. That's the amount of potential energy stored in the capacitive plates. Okay. Now, next, what we do here is throw this switch to B. That means, instead of A, we throw this to B, which means now the battery is out of the circuit. So our circuit here just like this. So what happens here is, as soon as we throw that switch to position B, then capacitor starts discharge. Okay. What we have here is the energy that is being stored in the capacitor will then basically convert it into the energy inside the inductor. Okay, so there is no resistor to dissipate the energy stored in the capacitor. Remember, so if you have an RC circuit, the resistor basically completely dissipates the energy inside the capacitor. What we have here is we have a capacitor and inductor. Both are devices that store energy. Capacitor stores electric energy, inductor stores magnetic energy. And this energy then will start in the beginning, right, as a purely electric potential energy. But then as we throw the switch to position B, this energy then will be converted into magnetic energy. Because what we have here is now there's an inductor that, as you know, going to start opposing, right? And it's going to just basically start converting all that energy that we have as electric into magnetic energy stored inside the, remember, most of those, the self-inductors are solenoids. So the magnetic field lines inside the solenoid. All right, so let's look at some of the mathematics over there. So that means what we have here is the energy. So the potential energy is in terms of like electric or magnetic. So you can write it as delta E, delta UE plus delta UB equals 0. Now, what we have here is we have two devices that basically store energy but don't dissipate energy. And they convert energy. That means, as the current kind of runs in the circuit, so it kind of goes in a cycle. So first, all the potential energy in the capacitor converted into magnetic energy, then all the magnetic energy in the inductor converted into electric energy inside the capacitor. That means what we have is just basically sort of like a back and forth. Now, that means what we can do here is there's a conservation of energy. Changing potential energy, changing electric potential energy plus changing magnetic potential energy equals 0. So from here we can write it as d dt of both of those type of energies, where we if you remember, the energy is q squared over 2c, then plus magnetic energy is 1/2 Li squared. And I'm not writing q max and I max because as a function of time, it technically changes. It goes from maximum charge to 0 charge, then from maximum current to 0 current. That means it kind of like fluctuates back and forth. So then this is equals to q over c, then dq dt plus Li di dt. And this is equals to 0. Okay. That means from here we can rearrange, remembering that current I is equals to dq dt. Okay. That means if I'm looking at di dt, this is equals to d dt of dq dt. That means becomes d squared q dt squared. Okay. That means what I can do here is this guy here can be replaced as a d squared q dt squared. So then if I come back and say, if I write it down in terms of q over c dq dt plus Li d squared q dt squared equals 0. So basically what we can see here is pretty much an oscillation, right? So right, so then substituting and rearranging, we get d squared q over dt squared is equals to negative 1 over LC times Q. All right, so now if I take this, the idea is that you can see that this is very similar to the d squared x dt squared equals negative k over m x. That means if you want to try to find the solution for this, we can see that it's very similar to something that we already done before, which is simple harmonic motion. And the solution for simple harmonic motion was the second order derivative of the function x is equal to the negative some constant times the function itself. Okay, so and then the solution for that was that x was equals to some a cosine omega t plus phi. This was the solution for that. That means one thing we can do here, similar way, we can assume that because it's exactly same format, taking 1 over LC to be constant, you can have on the left side the second order derivative of q with respect to time, on the right side of negative of the q. That means it's basically exactly same format. So we can say that, all right, then q is equals to some amplitude. In this case, basically, remember, a represents maximum displacement technically. So here we have then maximum charge. So q max, then times cosine of omega t plus phi, where omega for the case of the simple harmonic motion was the square root of the constant in front of x. That means this was equals to square root of k over m. That's what was the omega is equals to. That means here we can say then the omega same way is equals to the square root of what we have, in front of q on the right side. That means the square root of 1 over LC, or you can just write this as 1 over square root of LC. Okay, so this is basically the angular frequency or natural frequency of oscillation of LC circuit. Okay, remember, as I said, right? So basically what we're going to get here, we're going to have a sort of like, let's say, oscillations in our circuit, which I'll talk about in the next slide, where the energy basically goes back and forth between magnetic and let's say electric. So it's goes from fully electric to fully magnetic, then fully magnetic back to fully electric. So kind of like basically cycle very similar to the simple harmonic motion of a object going back and forth between plus minus amplitudes. So we can see that this is being the the frequency, right? So the natural frequency of oscillation of the LC circuit. So then we can say that I is equals to dq dt, since this is basically the equation for the q. So the solution for our differential equation, where q is equals to q max cosine omega t plus phi. That's how the charges for the capacitor change. Then we can also write this in terms of then the current, which is equal to dq dt. That means if I take the derivative of the q cosine omega t plus phi, I will get then q max, then derivative of the cosine omega t plus phi, which will be then negative sine omega t plus phi, then the derivative of the argument inside, which will give me then omega out of that. That means what I get here is, I can say AI as a function of time, right, is equals to, where I can take then q max times omega to be my maximum current amplitude. So negative I max, then sine of omega t plus phi. That means this is basically my I max. So omega times q max. All right, so that means this is the solution for the time varying charge and time varying current in the LC circuit. So we can see more or less what's going on right here, right? So very similar to how the spring is stretched to some distance a, then let go, and just basically oscillates back and forth. So let's say start from here when you take the the block and stretch it to some distance a, then let go. Before you let go, if you look at your total energy, the energy is basically all potential energy, remember, right? So then in this case, you can say analogous, at that instant, if you have, this is the circuit where you have a capacitor here and an inductor over there. So at that instant, let's call that a t equals 0, right? All the energy here is, stored in an electric field of the capacitor. At that instant, there is no, let's say, current in the circuit, because this is basically, let's say, as soon as you close the switch, right? So all the energy, or you can think like before you close this, close the switch, you throw the switch from B to A, or sorry, from A to B. There is no current in the circuit, and all the energy is across the capacitive plates. Okay. Then once we, throw the switch from A to B, then all the energy across the capacitive plates, right? But all that energy is basically start converting into the magnetic energy. Then at some point, kind of similar to when the block reaches the equilibrium position, remember, then all the potential energy, this was basically in terms of total energy, equals potential energy So let's say spring potential energy plus kinetic energy. That means here this is x equals 0. When the object gets to x equals 0, all the total energy is then is purely kinetic energy. So at x equals a, which is the amplitude, all the energy is purely potential. And when the black reaches x equals 0, all the energy is then purely kinetic. That means at some later time, when all the charges basically dissipate, right? Or, basically, you discharge the capacitor. So then what you get here, Q equals 0 and I is equals to I max. And then all the energy here is now stored in the inductor as a magnetic energy. Okay. But then because of the oscillatory, let's say properties of this circuit, the energy doesn't remain magnetic in the inductor. So then it starts converting back to the electric potential energy. Just like the black doesn't just stop here, and it continues moving, right, from x equals 0 to x equals negative a. And then here at x equals negative a, the energy here again, spring potential plus kinetic, then this is 0. Again, all the energy is purely potential. The same way, you know, at some time later, all then magnetic energy is converted to electric energy. And you can see, right, the polarity change. Now you have, let's say you had the positive plate was above, negative plate was below. Now, after it's converted from magnetic to electric energy, you have a change in polarity. So the positives at the bottom, negatives are at the top. And again, all the energy is purely electric potential energy. And then you kind of can go back around, because now the direction of the current would change, because what you have here is the polarity changes, right? Then the magnetic field direction change inside remember what we have is that the inductor always tries to oppose this current change, right? Because when you start with no current in the circuit, and then suddenly the capacitor becomes like a battery and provides energy to the circuit, inductor opposes that by basically inducing its own current and EMF, and then which then converts all that charges inside the capacitor on the capacitor plate into basically magnetic energy. Or, as those charges move, right, all their potential energy converted to magnetic potential energy. All right, so that means you basically have those are as extreme points, right? So that means this represents either purely electric potential energy, and then here purely magnetic potential energy, and then back again to purely electric, and then back again to purely magnetic energy. But obviously at some point, just like when you can have the black not at those extreme points like plus minus a or x equals 0, at some random x it will have then some potential energy and some kinetic energy, but they're not maximum. They're not maximum potential, not maximum kinetic, but they're, the sum of the energies will still be exactly the same. For example, your 100 joules is the total energy of the system. It will never change, regardless if it's purely kinetic or purely potential or some kind of combination of, let's say, 50 plus 50. Okay, that means at some point you can have combination. Maybe in this case it's 70 and this is 30, but still you get, the total is exactly the same before and after. All right, so and if we try to then plot the Q max, I max, and then also the energies, what we basically will get here is sinusoidal, graphs, right? Because what we get here is, remember, right? So the Q is equals to Q max, then cosine omega t plus phi. So then it's a cosine graph like this. And then I was equals to then negative I max, then sine omega t plus phi, which means that it's a negative sign as a function of time, right? It's kind of similar to the velocity of the simple harmonic motion, because when you take the derivative of the position, you get the negative sign. From the energy point of view, both of them are going to be positive, because you're basically squaring them, right? So since you're squaring both of them, what you get here, you get, so the energy that fluctuates back and forth, right? So you have maximum potential energy, then you have no electric potential energy, then you go to maximum. But one thing we can see here is this represents combination. Remember, these two together is equals to the total energy. When energy is purely potential, electric energy is purely potential, magnetic energy should be zero. When electric energy is purely zero, magnetic energy should be then maximum, and back and forth, right? That means, what you get, you have q square max over 2c, or li square over max over 2. Those are basically your maximum energies. That means ue is equals to, in a way, u max, and then you can see, right, cosine omega t plus phi. But in terms of, like, let's say, such that it's always positive, so kind of like squaring that, because q is squared, right? And then same thing, ub is equals to ub max, and because you're squaring this, right, the negative goes away, so then you have sine of omega t plus phi. Okay, well, u max is basically given with that, li square over max. So this is your ue max, this is your ub max.